Now let's consider the case of a second order low pass Butterworth filter. Most often this will be asked as an essay question for the examination. The idea, of course, that you must make yourself, but you will have to present this idea in an organized manner. In the beginning, a introduction pole oru cheriya sentence ezhuda. The second order low pass Butterworth filter is a low pass Butterworth filter having flat response in both pass band and stop band, such that it has a characteristic high corner frequency, often labeled as say FH. If the frequency of the input signal is below FH, it will be allowed to pass through it, whereas if the frequency is exceeding the characteristic high corner frequency FH, it will be attenuated. In the stop band, it will offer a gain roll-off of 40 dB per decade due to the presence of two filtering units present in the circuit. Such a filter is referred to as a second order filter. Now you will have to draw the circuit diagram for the second order low pass Butterworth filter, then explain the circuit, then working of the circuit, then make a qualitative analysis of the gain as well as the frequency response, then make your inferences on the basis of your analysis and conclude. So this is the circuit. In this circuit also the op-amp is in non-inverting configuration, so the signal is given to the non-inverting terminal, and to the inverting terminal you have the gain fixing resistances, say R1 and RF. R1 is grounded and RF is connected to the output terminal. Plus VCC and minus VEE are shown, and to the non-inverting terminal we have shown two units of passive RC filtering components having resistances R1 and R2, capacitances C1 and C2. For the first unit, the capacitor C1 is connected to the output point, whereas for the second unit, the capacitor C2 is connected to the ground terminal. So this is a passive filtering unit having corner frequency 1 by 2 pi R1 C1, and this is another passive corner pole circuit having corner frequency 1 by 2 pi R2 C2. Now we will look into the working of the circuit. This will have a natural frequency, that is FC equal to 1 by 2 pi R1 C1. Basically this is a pole such that it will allow all frequency less than its characteristic corner frequency or natural frequency to pass through it, and if the frequency is exceeding the corner frequency, it will be attenuated at a roll-off of 20 dB per decade. This signal allowed by the first unit is injected to the second pole having corner frequency 1 by 2 pi R2 C2. If the frequency of the input signal is less than the corner frequency of the second pole unit, it will be allowed, or it will be coupled to the non-inverting terminal of the op-amp. And if the frequency is exceeding frequency of the input signal Vi is exceeding the corner frequency of the second unit, it will be attenuated. The signal reaching the non-inverting terminal of the active component will be amplified at a gain of 1 plus RF divided by R1. For a second order Butterworth filter, the midband gain has a particular value. The gain of a filter, that is a Butterworth filter, is given by the empirical formula. This is the formula that we have solved from the general formula A equal to 1 by value of the polynomial Pn of S. Here this is found to be 3 minus 2k, where 2k is the coefficient of S term in the relevant Butterworth polynomial. The Butterworth polynomial of order 2 is S square plus root 2 S plus 1. Clearly, the coefficient of S is root 2, that is 2k. So the midband gain is given by the expression A equal to 3 minus 2k becomes equal to 3 minus root 2. Root 2, as you know, is 1.414, 3.000 minus 1.414. 10 minus 4, 6. This is 9 minus 1, that is 8. 9 minus 4, that is 5. 2 remains here, 2 minus 1. So, the midband gain for a second order Butterworth filter response is 1.586. So, unlike first order filter, you cannot have any value for the midband gain. The midband gain must be 1.586. Now, we have seen that the signal that is being allowed by the first unit will be allowed by the second unit also, or the signal that is being allowed by the first unit only will be injected to the second unit, but we require both these units to have the same natural frequency. The general expression for the natural frequency of these two units of passive filter is 1 by 2 pi root R1 R2 C1 C2 as a special case, such that the signal that is being allowed by this one must be allowed by this one also. We will make this approximation practically, that is R1 equal to R2 equal to R and C1 equal to C2 equal to C. Then the expression for F becomes, that is the expression for the characteristic corner frequency FC, or the characteristic high corner frequency of the second order filter, FH, is equal to 1 by 2 pi RC. And the midband gain that follows the general empirical relation for gain of Butterworth filter, AF equal to A by root 1 plus omega by omega C all raised to 2n, where you have to substitute n equal to 2. ഇപ്പോൾ നമ്മൾ കണ്ട A എന്ന് പറയുന്നത് midband gain ആണ്. Second order Butterworth filter response കിട്ടണമെന്നുണ്ടെങ്കിൽ midband gain 3 minus 2k equal to 3 minus root 2 equal to 1.586 ആവണം. അത് മസ്റ്റ് ആണ്. അപ്പം മാത്രമേ ഫ്ലാറ്റ് റെസ്പോൺസ് സ്റ്റോപ്പ് ബാൻഡിലും പാസ് ബാൻഡിലും കിട്ടുകയുള്ളൂ. ഫിൽട്ടർ ഗെയിൻ ആണ് AF, ദാറ്റ് ഈസ് ഗിവൺ ബൈ A by root 1 plus ഒമേഗ എന്നുള്ളത് 2 pi f എന്ന് എഴുതാം. അപ്പൊ ഇത് F by FC or F by FH all raised to 4 എന്നാണ് വരിക. ഇതിലെ എയുടെ വാല്യൂ ആണ് നമ്മൾ ഈ പറഞ്ഞ 1.586. Now on the basis of this we make an analysis. For that we tabulate these values by fixing A as 1.586 and we take the corner frequency as 1 kilohertz. Now we tabulate. Of course you can have an additional column on the left labeled with the serial number. First one, F, the frequency of the input signal, F by FC, the frequency of the input signal divided by frequency, the characteristic corner frequency, raised to 4 is here, and decibel gain, AF decibel equal to 20 log A, that is 20 log 1.586, which is 0.2. So the midband gain of this amplifier is very small. Minus 10 logarithm of 10 comes from this, say 20 logarithm of root of 1 plus F by FC raised to 4. That is 20 into half logarithm of 1 plus F by FC all raised to 4. That is 10. 20 into half make it 10 logarithm of 1 plus F by FC all raised to 4. When the frequency is 0.1, F by FC is 0.1 divided by 1k. That is 10 raised to minus 4 all raised to 4 is there. 10 raised to minus 4 all raised to 4 is 10 raised to minus 8. That is 0.7 തവണ 0 പിന്നെ ഒരു 1, which is to be added with 1. 1 plus 0.00001 എന്നുള്ളത് approximately 1 തന്നെയാണ്. അപ്പോൾ 0.2 minus 10 log 1 എന്നുള്ളത് 0 എന്നാണ് വരിക. Now we make frequency 10 times increased. ഇപ്പോൾ 0.1 എന്നുള്ളത് 1 എന്നായിട്ട് മാറി. 10 raised to minus 3 എന്ന് വരും. 1 by 10 raised to 3. 10 raised to minus 3 all raised to 4. അതും 10 raised to this is 10 raised to minus 16. ഞാൻ മൈനസ് 8 എന്നാണ് പറഞ്ഞത്. അപ്പോൾ 3 പോയിന്റ് കഴിഞ്ഞ് 15 പൂജ്യവും പിന്നെ ഒരു 1 ആണ്. That you can safely take to be approximately 1. Here also this is 10 raised to minus 12. That also can be safely taken to be 1. 10 log 1.00000000001. That is 0.2 minus 10 log 1, which is 0.2 itself. Now again we make frequency 10 times greater. It becomes 10 hertz. Then this becomes 10 divided by 1000. That is 10 raised to minus 2 whole raised to 4. Here now it is 10 raised to minus 8. That also can be taken to be safely 1. Now we take the frequency becomes equal to the corner frequency. Then f by fc is 1 raised to 4. 1 raised to 4 is 1 itself. So this is 1 plus 1, 2. So the decibel gain will be 20 log 1.586 0.2 minus 10 log 2. That is 3 decibel. So this is the frequency at which the gain reduced by 3 dB comparing to the mid-band gain. For this is the minus 3 dB frequency for characteristic frequency or resonant frequency or natural frequency or characteristic corner frequency or characteristic high corner frequency of the Butterworth filter for the filter. And again we take the frequency 10 times incremented. Then f by fc is 10k by 1k, that is 10 raised to 4 is here. The midband gain will be, the gain will be then 0.2 minus 10 logarithm of 1 plus 10 raised to 4. 10 raised to 4 is 10,000. 10,000 plus 1 is approximately 10,000 itself for logarithm, for taking logarithm. So this is logarithm of 10 raised to 4, that is 4 into 10, 40 decibel. So frequency, once the frequency of the input signal beyond the corner frequency incremented by 10 or become a decade increment, the midband gain, the gain is reduced by 40 decibel. 0.2 ആണ് മിഡ് ബാൻഡ് ഗെയിൻ ഉണ്ടായിരുന്നത്. അതിനേക്കാളും 40 dB കുറയാണ് ചെയ്തത്. ഇതാണ് സെക്കൻഡ് ഓർഡർ ഫിൽട്ടർ റെസ്പോൺസ്. അതൊന്ന് ഒക്ടേവിൽ എങ്ങനെ വേരി ചെയ്യും എന്നുള്ളത് നോക്കാനും വേണ്ടിയിട്ട് we make a two-fold increase of frequency. 10k becomes 20k. Then f by fc is 20 divided by 1k, that is 20 raised to 4 is here. Then the gain is 0.2. 20 log a is 0.2 minus 10 logarithm of 1 plus 20 raised to 4. 20 raised to 4 plus 1 is approximately 20 raised to 4 for taking the logarithmic operations. Then this is 4 log 20. That is 4 into log 20 is 1.3010. So this becomes 40 into 1.3010. That is 4 into 13.30. That is 52.12. So when the frequency becomes incremented by two-fold from here to here, the gain become reduced by an amount of 40 minus 52, that is 12 dB per decade. So a roll-off of 40 dB per decade is identical with, I told it 12 dB per decade, it's not 12 dB per decade, it's 12 dB per octave. So a roll-off of 40 dB per decade is identical with the usage of a roll-off of 12 dB per octave. Again we increase the frequency up to a very large value of 1000k. Then this becomes f by fc is 1000. So f by fc all raised to 4 is 1000 raised to 4, that is 10 raised to 12. Then the gain will be very small, extremely small, of the order of 0.2 minus 10 log 10 raised to 12. That is 12 into 10 120. 0.2 minus 120. It's an extremely small gain where the amplifier is offering a gain less than 1, a gain extremely less than 1, and is of no use. Such a signal will be then attenuated, of course. Now on the basis of this analysis we draw a filter response. Log frequency is taken along the x-axis, decibel gain along the y-axis. As the frequency increases, the gain remains a constant till Fc is reached. Beyond, at Fc, of course, at Fc, the gain is reduced by 3 dB. So this is the corner frequency. Beyond Fc or Fh, the gain will be falling at a rate of 40 dB per decade, which is